Hey guys, Colin here, hope you're well. So today I'm going to show you a super interesting sample that was sent to me from a guy on Twitter called Arti Karahoda. Cool guy, you should definitely give him a follow. Goes on Twitter at WizCap. And he sent me this sample which I found really interesting and I thought would make a good video because it uses a lesser known technique, probably what I'd describe as an old school technique for executing macros from a malicious Excel file. In this particular case, it looks like it's designed to deliver a Cobalt Strike beacon. And so what I wanted to show you today was firstly how to analyze this particular technique of code execution, and then also how to extract the shellcode and some of the tricks that the shellcode uses in order to disguise itself as well. So it's quite a packed video with some really interesting content that hopefully you'll find useful when you're threat hunting in your environment or if you're performing some malware analysis yourselves in your own labs. So this is the sample that we're going to take a look at, and Arti kindly sent me the link to the any run, and as you can see, basically it looks like the Excel file crashes, and in fact when I ran it in my own lab as well, that's exactly what I experienced. Was that I opened it in Excel, I ran it, and it crashed as well. So I had to kind of pick out all of the indicators. So I'm going to show you the process that I went through, and the various research that I kind of referenced from other people who've done an amazing job at kind of documenting these techniques that really, if you don't know about them, if you've never heard of them, you should definitely get up to speed on. So anyway, you can pull the sample down from here. I've got it the Excel file in my lab here, in my lab virtual machine. So let's just super quickly talk about the environment and how I get things configured, which is usually the same every single time I look at malware. So the first thing is I have my network traffic proxy through Burp Suite. So if you have a look at my proxy settings here in my my internet settings, you can see that my network adapter is using a proxy on localhost for port 8080, and that just gives me, so if you have a look in my options here, you can see that if I scroll up a little bit, if I make this bigger, you can see that this listener, this Burp Suite listener, will listen by default on port 8080, and of course it's not waking up because I'm doing a video and it doesn't want to play the game. Now here we go. So here we go. So you can see the proxy listener on 8080, and that will give you a nice easy view. If you turn intercept off, so that would be on. If you turn it off, you could just get a nice flow in the HTTP history of any kind of requests that get made from your network adapter. Notice though that not everything will abide by the proxy, and so you can still have network connections that go out across the internet that bypass your proxy. So just be aware of that in your analysis and use something like Wireshark or Microsoft Network Monitor or have you. Anyway, not ready to delve into too much of that in this particular video. Also, I like to use Process Hacker, and I like to use which just kind of gives me a live view of processes on the machine at the moment, so I can poke around them if I need to. And then also I run Process Monitor, and then so Procmon, as most people will know, gives you a view on what is going on your file system in the registry from a network perspective, pretty much everything that's going on your machine. And usually what I like to do is just filter out where the process where the operation is process create, and then also where the operation is process exit. So that's my kind of default, but then you can just filter stuff around that as well. So usually, bear in mind as well, just notice that I do use a VPN. So on my host, I tend to use private internet access. So I'm coming from a proxied IP address, just in case. I don't really want to leak my personal IP address to the rest of the world, and certainly not to malware operators. So you should definitely do that as well. You can also isolate your virtual machine if you want to, but sometimes you want to see the live internet connections as well. So we've got our monitoring set up. Let's give it a whirl, see what happens. So we'll open the file. And then really I'm just interested to see if I see the same thing as we saw in the sandbox on any run. So you can see the content of the file look like some kind of salary or financial kind of content, which would be potentially juicy, and you might want to see the stuff behind it. And it's all kind of like part of the fish to get you to enable the content to synchronize the data, which may or may not be spelt right. I can't really work that out. So macros have been disabled. We'll just enable them. We'll see what happens on our machine. You can see that Excel kind of thinks about stuff. and then ultimately crashes. If we have a look here, it's just the usual kind of @crash message that we get in Excel. Not very helpful. If we have a look in sysinternals here on procmon, the tree view, we see very similar kind of processes that were spawned like we saw in the any run, right? So they saw DW20 and then DW win as well, which is exactly what we're seeing here. So the Watson client, it's just a basic Microsoft crashing processes. If I go into Burp Suite, I don't see anything. This entry is just from when I open Process Hacker, checking for updates. So unfortunately, it doesn't look like this malware is executed in my environment here just now. But that's not to worry, because obviously we're good malware analysts, right? And we're going to statically analyze this and see what happens and pull out all of the indicators. So let's just get rid of process monitor for now. We don't need that. And let me just clear. And my machine decides to wake up, we shall clear our history here in Burp Suite. There we go. And then we'll take another look at this and see what happens. Now, obviously, as you notice, we had to enable macros. So you would think if you just go into Developer and into Visual Basic here, you would see some macros. But you'll notice there's no macros in the VBA editor. And there's a good reason for that. That's because it doesn't use VBA macros. There are macros at play, they're just not VBA ones. And this, when I said to you before about this being an old school technique, well, Microsoft, in its infinite wisdom, supports something called XL4.0 macros, otherwise known as XLM. Not to be confused with XML, the common kind of syntactical language, what have you. But XLM, XL4 macros are something that you should definitely get to know about, because these are super powerful, but actually really problematic for the likes of antivirus vendors and other such security tooling to detect. So really interesting. And the way it works, let me probably easier to show you a new document before we dive into the malware. But if you, rather than if you were going to write some Visual Basic, as I say, you would usually go in the editor and write some code and stuff. But instead of that, what you can actually do, if you right click on your sheet 1 here, go to insert, you can see here you can insert a sheet that's a macro sheet, a macro XL 4.0 macro. So we'll insert that, and we can type in stuff like this, and these are commands which will be executed. Now if we right click on this and click on run, and it's going to run from the current cell, you can see it's going to execute that command that we give it. So in this case, obviously it just pops calc, but there are a bunch of different commands and functions that XL 4.0 support, this kind of macro 4.0 supports. And there's too many to go through. However, what I will point you to, let me just go to Chrome here, is an amazing resource which I found through browsing, and I will link this in the video. This particular PDF has basically every function and all of the syntax and stuff like that behind it that you can think of, and we'll reference this in just a second in our research or analysis of this particular file. So that's how it works. And then notice as well, what you could also do, let me do something else. So you can do like 2 commands, and you need, to stop it complaining, you need like a halt or a return command at the bottom. But if I execute this, I'm executing the first cell, right? So row 1, column 1, which is R1, C1 here, right? So click on run, you can see that calc popped, but also this message box or this alert box popped up as well. And so the way that XL4 works is that it's going to execute this command in row 1, column 1, then it's going to go to row 2, column 1, and it's just going to go top down, left to right, and execute anything that's in this worksheet column. And then you can reference other columns, you can make it jump around and all the rest of it. But that's the kind of execution flow, the same as any other programming language really. Top down, left to right is what the code is going to execute. So anyway, let's just clear the contents and let's go back to our malware and have a look and see what it's doing. Now in this particular case, this is just a worksheet and it's not an XL4 whatever you call it, macro sheet. But you'll notice if you right click on sheet 1 here, you can unhide, and they've hidden a sheet here. So always check for that in your analysis. So let's unhide the sheet, and you can see that we're somewhere down. You can see a few there's a bit of text over here in column 100, what have you, onwards, and there's also some text all the way over here that says enable content to upload the file format. So you would think that's probably maybe some lame part of the fish in case you just did happen to stumble across this particular worksheet, then it's just going to tell you to upload the content, and you might not look all the way over here in your analysis at the other columns because it starts at like 100. However, also note that when we executed, beg your pardon, when we enabled macros, the code seemed to auto execute. And so we want to essentially find the entry point. We want to find, what's the initial instruction that's going to get executed. And if you drop down here, you'll notice that one of the cells has been renamed as auto open. And so if you do that, if you enable the same as if you were writing some VBA, you would declare a function called, or a subroutine called auto open, and that would be the subroutine that gets executed when the malware opens. So the same applies for XL4. So if you name a cell in a macro worksheet as auto open, that's going to be the first one that executes. And so you can see here that it pointed to this one here, this cell, which is in row 5, column 102. And all that seems to be doing is concatenating a few different strings together. So you can see row 1, column 102, which is that one, row 2, column 102, that one, row 3, and row 4. And it just builds the string VirtualALock. Well, that's obviously suspicious, and will give you an idea of what's going on here. So you would imagine that this code is going to use VirtualALock at some stage. But just concatenating a string isn't doing anything malicious. But like I said to you before, the code will go top down, left to right. So it's going to start here, and it's going to move on to the next instruction, then the next instruction. And so you can see here that it's going to activate the update workbook, which is this one. And then it's also going to jump to row 1, column 103 and execute. And row 1, column 103 is here. And so you can see here that the next instruction is error, false, and then there's a range here. So if we go back, and we'll go back to this cool resource. Let me just do a Control and F on error, and then we can jump to it. So this, you can see the function in XL4 specifies what action to take if an error is encountered while a macro is running. And so use error to control whether XL messages are displayed, or to run your own macro when an error is encountered. So if enable logic, which is the first parameter to error, is 0 or false, all error checking is cleared. And if it's cleared and an error is encountered while a macro is running, XL will ignore it and continue. And error checking is selected again by an error true statement, or when the macro stops running. So if you look back here, you can see here that indeed it is false. So it's going to clear all the error checking, and it's just going to, if it encounters an error, it's just going to push on ahead. So it's the kind of, I feel like this is a similar thing to saying like on error resume next, that kind of statement in VBA. And then we see the range, right? So which is row 2, column 103 to row 3, column 103, which are these two cells. So the first one is this string, which is obviously a file path, Microsoft Office appx manifest.xml. And I've never heard of this, and even when I Google it, let me just Google it again. You can see here that I don't really get any proper results with it, and maybe one of you guys can help me understand the relevance here. But what I think is happening, if I go to the next cell in the execution change here, it tries to open this whatever is listed in row 2, column 103, which is this. So it's trying to open that XML file. And if we go back to our super cool reference here, have a look at fopen, you can see that it's in the access num parameter, which is 1 to 3. So in this case, it's 2. So it's trying to open in the file with read-only permissions, right? So it's trying to open this XML file with read-only permissions. But certainly on my machine, that doesn't exist. And so the next check that gets made is if is error row 3, column 103, so the call to fopen, then jump to so if we have an error, which in my case we would do, we're going to jump to row 1, column 100, which is here. Or if we don't have an error, row 1, column 104, which will be here. So we've got two kind of paths here in this if condition. What I'm also going to do, just quickly, just to try and make things a little bit easier to read, hopefully this has worked. Let me scroll all the way over here. Yeah, so rather than it's all a zero showing, I've just copied and pasted the values just so you can see without having to click into each cell. We can see a little bit easier what's going on in each of these cells. So this is where we were, right? So this on error. So if is error, the call to F open, jump to row 1, column 100, if not 104. And so we just want to quickly have a look and see what the kind of main differences are between these two branches. So we can see here there's a call to call, which is in a function within XL4 that we can have a look at the documentation for shortly. It looks like it's calling kernel 32 with another parameter passed to it, R5, row 5, column 102, which is where we are now, right? So I beg your pardon, where we started, which was the concatenation of VirtualALock. So we're just going to call kernel 32 and get the address space of VirtualALock and then execute VirtualALock as well. And you can see here that we've got a weird string, right? 5 J's. And what that means is that the J in XL4 is a data type, and in this particular case it's a long integer, and the first one that you feed it is going to be the return type from this particular call. So we're expecting a return type from this function as a long integer, and then the next 4 J's that we're going to see are also long integers, but they are going to be the arguments that get passed to the particular function that you're calling. And it seems a little bit confusing. And it is, just because this is probably syntax that isn't particularly common. However, just kind of go with it, I guess. What I will point you towards is some research. Actually, it's probably a good time to talk about it now. So let me go back to Chrome here. And there is an amazing blog from Outflank. If you've never read any blogs on outflank.nl, then definitely go and check them out. Also, these were the guys that authored Evil Clippy, which is one of my favorite tools for analyzing and also creating malicious documents for testing purposes, obviously. But anyway, they describe the techniques that we're talking about today in a massive amount of detail. And you can see that actually, when you look at some of their proof of concept code, it's very, very similar to what the bad guys are using. And in fact, Stan, I think he wrote this blog, details some of the techniques that he used in order to inject a Cobalt payload into an XL4 macro. So some of there are some differences though. In fact, one of the key differences here is you see that instead of in our malware we can see equals call kernel 32 blah blah blah. We can see here that in the Outflank blog there's a call to register. And firstly, what that's essentially doing is registering a name or a wrapper for a particular function, and it's just going to give it a name. And in this particular case, he calls it VirtualALock. And then the next line, you can see here, he just invokes VirtualALock, i.e. the function that's just been registered, and passes in all of the parameters to VirtualALock. All our code is doing is just combining those two instructions in the blog. So the register and then the call, you can actually just all do it via the call. You can just call whatever in kernel 32, so VirtualALock, and then you can just feed it all of the parameters as well. So you can see here that on this side, the same thing as well. So depending on which execution path that you take, and in fact, we'll follow this one just because maybe the API calls are a little bit more familiar to people. So VirtualALock, all of the J's, and if we have a look at what we want to do is have a look at spell it right, VirtualALock. Have a look at the arguments that get passed to VirtualALock, and we can understand what they mean. So the first one is the address, so the starting address of the region to allocate, and we can see here that the first parameter is 0. So it's just gonna let the operating system decide. If this parameter is null, the system determines where to start the allocated region. The next is the size, so the size of the region in bytes that's going to be allocated. So we can see here 880 bytes that we've asked for. And then the next flag is the FL allocation type. And so bear in mind this is in here 4096, it's in decimal. So because I'm rubbish at hex to decimal, or decimal to hex rather, let me do that, decimal to hex. 4096, convert that to hex. We can see it's hex 1000. So we can see that the parameter is this one, and allocates memory changes from the overall size of the memory and the paging files on disk from the specified reserved memory pages. Okay, so that sounds good. And then the next parameter is 64, which, let me have a look, what is it to do with, is okay, FL protect. So that is the, jump down here, go. The memory protection for the region of the pages to be allocated, and so it can be any one of the of these particular constants, and in this particular case, we'll have a look here. What was it? 64 in decimal rather, which is 40 in hex. If you have a look at 40, it's going to it's going to allocate virtual memory with page execute read write permissions, which is very, very common in terms of process injection. So that's cool. So we're going to call that first. Then it's going to select a range of cells, and you can see the range of cells that it's being selected. So on this particular branch, it's selecting row 1, column 105 to row 1000, column 105. So basically all of this stuff here. And then it's going to make the active cell row 1, column 105. So it's just going to it's going to select the range, but also basically put the cursor in the first entry in that cell as well, in that range as well. So it's made that selection, and so you can imagine, you can see here that all of this char code stuff, so equals char 217 plus tar 225, etc. This is all of the shellcode that's actually going to be executed by the malware. So it's going to set the value in row 1, column 99, which is over here, to be 0. And then we enter into a little loop here. So we've got a while loop, and the next at the bottom is going to be the iterator through the loop. So whilst the length of the active cell is greater than 0, so you're in this cell first to begin with, and then we're going to imagine that we're going to jump down through the course of the loop until it gets to a cell which is not greater than 0, i.e. an empty cell. So it's just going to loop through all of these, and then it's going to make a call here to kernel 32, write process memory, and then if we make this a little bit bigger, we can kind of see what's going on. Even bigger again. Here we go. So we can see here the call to write process memory, and we have these data types that are passed in as the parameters to the call. So the first J is going to expect a long integer, and then the rest of them are the different types that of the arguments to write process memory. And here are the comma separated arguments that are going to get passed in. So if we have a look at write process memory, here we go. We can see here the first argument is the handle to the process. So a handle to the process memory to be modified, and that must be read write permissions. So in this case it's -1, and then R2C104, 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay, yeah, so the second parameter, so R2C104, which is row 2, column 104, which is this one here, which is the call to VirtualALock, right? So the return, whatever was returned from the call to VirtualALock is going to be in this particular buffer, if you like, plus a load of zeros. So in this particular cell, we set the value of row 1, column 99 to be a load of zeros, and for whatever reason, it just adds a load of zeros to it. So that's the second parameter to write process memory, and that's the base address. So it's the return from. Let me have a look here. Are we on VirtualALock? The return value, you can see here, the return value is the base address of the allocated region. So we're obviously going to start from, we want to write the process memory from the base address of the memory we just allocated in VirtualALock. And then obviously, what do we want to write? The third parameter is the buffer, so a pointer to the buffer that contains the data to be written in write process memory, and that's obviously the active cell. So we're going to loop through each of these and write each of the lines of text, or whatever this evaluates to. We're going to write that into the buffer, and then how much are we going to write? So the next, you can see here, the next parameter is the size, so the number of bytes to be written. Well, that's obviously the length of the active cell, and then it's going to iterate through that list. Okay, so and then it's just going to do that until it reaches where the active cell is not greater than 0. So it's almost like a do while loop that we're in here. And then once it does that, you can see here, it's going to call create thread in kernel 32. And what's it going to create? Well, it's going to create a thread from the memory address space that we just allocated and then filled up with the buffer from write process memory. And then it's going to jump to row 11, column 100. So if we go all the way back to row 11, column 100, which is here, it's going to produce a formula on this particular, this part of the page, some kind of message, and then going to activate sheet 1 again. So basically we're going to finish. So the question is though, what's this doing? What is all of this shellcode, and how can we, this is all charcode stuff. How can we convert this into shellcode? Well, firstly, what I would suggest is we get friendly with CyberChef. So let's do that now. So what we should do, come on CyberChef, wake up. There we go. Right, just if we copy it properly. Oops. Ugh, why is my copy paste buffer not working? Copy. Cannot empty the clipboard. No, of course you can't. That's annoying, isn't it? Let me see whether I can do it any other way. Here we go. Right, that seems to work. Okay, so what we should do here, really we want to we don't want all this char nonsense, because this is just a big string of text that we put in here. We just want to extract the number that's in between them. So we can use a regular expression to help us with this. Why is my machine going crazy? What am I running that's making my machine go crazy? I don't know. So what we can do is like, I completely stole this from, I'll show you, regex between strings. I won't take any credit for this regular expressions because I'm absolutely rubbish at creating them. But you can see here that like this dude wants to know, how can I get match every character between this is and sentence. So he just wants the middle bit. So if we take that kind of syntax, apply it here, but obviously we don't want this is. We want stuff that's between char and open bracket, and whatever's between a close bracket. That one. Okay. But then we just want to adapt it slightly because we don't want to make it quite as greedy. There we go. So you can see the matches are all highlighted. If we list the matches, just to get a nice view on what's going on, we want to treat them as decimal. I can spell decimal. There we go. There we go. With the delimiter as a line feed. And then we want to change it to hex, because that's where the money is, right? So 2 hexadecimal. There we go. So there's the hex of our shellcode. And also what you can do in here is disassemble it actually. So 32-bit shellcode. So here's our shellcode. But you'll notice that it doesn't really look, there's some instructions in here and I've got some question marks and stuff like that it doesn't really decompile well, and I'll show you why. What we should do, take that out, copy it. Hopefully my copy paste will work. We'll see. Let's jump down here, go into HXD, create as a new file, copy it in, save it, and we'll call it shellcode.bin. So we've now got shellcode, which is position independent code. We need a way of converting this into an executable, put an executable wrap around it in order to then debug it, to run it and debug it. One of the tools that I like to use is from Hexacorn, who developed a super simple bat file. And it's called shell2exe. So I'll share the link where you can get this from his website. I'll just extract it here to my desktop. So he's got a cool little bat file. Let's open a command window. Shell2exe.bat. You have to specify the architecture, whether it's 32 or 64 bit, and then just feed it shellcode.bin. And then it's done. It creates me a nice little exe wrap around that shellcode. So now, if we stick it in x32 dbg, my machine's going crazy. My fan's going crazy. I must be doing something in the background that it doesn't like. Anyway, so now we can stick it into x32 and we can do some analysis on it. So there's some instructions here that I'm not familiar with, and I'd have to go and Google. I don't know what FABS means. Probably something to do with ABS being the absolute value of something, but I don't really know. But the first meaningful instruction is like moving this big hex value into EBX. I've no idea what FNSTNV means. So more instructions that I don't know. But straight away, what kind of grabs my eye is this XOR instruction. And you can see here that like what is being XOR'd is a buffer in EDI plus 14 and EBX. So let's just walk through the first few lines of this code together. So we can see here that that big value gets moved into EBX. Whatever that value does, I have no idea. Pop off EDI, that's got 0 in it. XOR ECX, that just makes sure it's cleared. And we can see here that D1 is moved into into the lower half of ECX, which is CL. And then we subtract this big hex number from EDI. So I'm no good with hex numbers, as I said. So let's convert here, hex to decimal. What was it? Well, FF, 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 FC. FF, 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 FC. We can see here that it's -4. All right. So we're going to subtract from EDI -4. So subtracting a minus number adds it. So we can see here that EDI is a memory location, 401-1000, which is our entry point. So if we execute that, we can see that it's increased by 4 because we've subtracted -4 from it. It's a bit weird. Hang on a second. I had to take a drink just in case I start coughing. Anyway, so we've subtracted -4, which is adding 4 to EDI. So if you think that puts us in here somewhere, right, in our memory space, right where we are, but then we're going to XOR the contents of EBX with whatever's in EDI plus 14. If we have a look at that, following dump address of EDI plus 14, you can see here, like, it's this memory address 401018 was right by where we are, and you can see here that the hex is BD 958325, and notice BD 95 B3 25. They're all of the following instructions, and then you can see we're in a little loop here, this little XOR loop, and so if you start to, let's take this next instruction, you can see here that as soon as you XOR that, those instructions change. So it's almost like the next instruction has been XOR'd, and now we're in a loop. And then so if we go back to the top of the loop, we can see here again it's going to subtract -4 from EDI, which is add another 4 to EDI. So watch the value here. It's going to go to 401008. So we're going to take the next 4 bytes. There we go. Then we're going to go, we're going to XOR whatever's in EBX with the contents of EDI plus 14. So you can see here that EDI plus 14 is down here, which is 40101C. So we're now here. It's going to start XORing this part of the code, so the next 4 bytes. And you can, and we're in the loop again. And then you can see that we're subtracting, we're XORing, and then looping all of the time. Which is really cool, right? And actually, what I failed to mention actually was that on each iteration of the loop, the bytes that you're XORing also get added to the key. So there's the XOR key, which is held in EBX. So it started off as this weird value here, but notice that the key on each time is changing. So you can't just use one key to statically un-XOR all of this stuff. You have to kind of go through the loop. So you can see EBX changing. So every time we're XORing the bytes, the output of which is fed back into to be the XOR key. And then we kind of loop through this XOR set, and you can see all of the code kind of changing beneath you. A little bit boring to sit there and do this manually. Just breakpoint on the instruction after the loop, press F9 and take your breakpoint off, and now all of this code has been un-XOR'd. So we've now unpacked the shellcode, and so we can actually poke around it and do something, and try and find out exactly what is going on. So you can see the next, out of interest, just to kind of go through it in a little bit more detail, the next instruction is this call to this particular memory location, F7 into it. And we can see here that some of these values are being pushed, and then there's a call to EBP, and there's some more calls to function calls, etc. What I would do, first off, and what I started to do, I start to think, well, these are weird values. Why would you push these weird hexadecimal values to the stack? So convert them from hex, and you can again use CyberChef for stuff like this. So when it wakes up, and so if we use CyberChef, we can quite easily convert the hexadecimal. So what is it? 7465.6e, 7465.6e, from, let's spell it right, from hex, and you can see the output is 10. But don't be confused by that, because these are being pushed to the stack. So they're being pushed, and that means they're going to be popped off the stack and read in the reverse order because of our endianness, our little endianness. So what we want to do is reverse the string, because they're going to be popped off in the reverse order. So actually what we've got is net, and then the next string 69.6e, I can't remember them all, 69.6e, 69.77, 69.77. So you can see win inet. And obviously that's the name of a DLL. So this is how it's resolving its DLL. So if we step through this here, we can see that in ESP, we can see the string being built up here, win inet .dll, and it's going to make a call to that particular function. And no doubt there are obviously a lot more APIs that it's going to potentially resolve as well. What you can also do, we still got our burp suite intercepting the traffic here. Let me restart the binary. You can actually just run this, and what you'll notice is that it will hopefully produce a C2 for us. So it's going to resolve its DLLs and all of the instructions and the functions that it wants to use, and then it's going to hopefully give us something to work with. You can see it's still running. In fact, last time I ran this, I got it balked on an error. So you can see I've got a first chance exception. Something's gone wrong. And I think actually that built into the shellcode is some anti-debug stuff. So it's probably throwing errors because it knows it's being debugged. But notice I had this C2 connection to wa.arla.com circle.gif. That when I first saw that, I thought, oh great, that's the name of the C2 address. And actually, if you go to it, just copy the URL. I thought, I'm sure I recognise the name Arla, and I do, because it's the brand of milk that I drink. And I thought, I wonder what this is about. Surely Arla's not been compromised and being used as a Cobalt C2, blah blah blah. And then I noticed, if you look down here in the request, the host header is a subdomain on azureedge.net. And so this looks to me like a prime example of domain fronting. Now, I'm certainly not an expert on domain fronting, and every time I read a blog about it, it confuses me. However, the basics that I understand are that you can smuggle the request to a content delivery network by using a genuine website like arla.com, for example, and because the host header doesn't match the request, i.e. the actual domain that you're requesting, then that's going to smuggle itself out through a network, because what you're going to see in your logs is a request to arla.com. That's probably going to be permitted. It's not going to be a website which is going to be blocked due to its category, etc. But actually the request is going to get forwarded by the underlying server to this azureedge.net subdomain. So definitely welcome some more research on domain fronting. But if you went to this particular subdomain, you will see that actually we get a 502 bad gateway. So it looks like in this, and that's what we got here in Burp Suite as well. So it looks like that the code behind that beacon has been taken down. And I think, I'm making an assumption here, I think that's probably why the shellcode or the Excel file was crashing. Maybe it didn't get to execute everything that it needed to. I'm not quite sure. It could be that the architecture of my machine isn't right for this particular environment that this Excel file is targeting. So it might have actually tried to execute the wrong type of shellcode or the wrong kind of API call. I don't know. Haven't done that fuller analysis yet. However, even though the kind of message really from this video and the whole point of it is, even when you run your malware in your lab, even if it crashes and if you're not getting any kind of potential infection, still perform that static analysis and still kind of get all of the indicators you can, because lo and behold, we've managed to get ourselves a network indicator here that we couldn't get from our behavioral analysis, and that's really, really key. And now you understand the kind of techniques the bad guys have used to smuggle their code in, the network style of request that they're making, blinking, etc. So yeah, really fun stuff. Really interesting sample. Thanks again to Arti Karahoda, who sent this over to us. I really enjoyed taking a look at it, and definitely look forward to your onward research and comments as well. So hopefully that's useful to you in terms of the techniques used and the tools and the systems and stuff like that. Yeah, we'll talk soon. Thanks all. Cheers.